Hello, class. Welcome to the Unit 5 Section 3-9 notes. I'm extremely sorry. I had a meeting today and I was unable to make it back to class in time. I thought that you were going to get your packets back, and I apologize that those were not given back to you as well. I decided to make this video so that you can get a head start while you're at home, and I can limit the amount of teaching on Wednesday. We're still planning to have the quiz on Friday. We can have a discussion further on Wednesday, but just follow along with these notes and maybe write them on a scrap piece of paper. And then when you get your notes packet back, you can transpose them over to the notes packet. So I'm going to try to make it as quick as possible, also explaining all the topics. Then you'll have this video to refer to before your quiz on Friday. This will also help out anyone who is absent from the day 1 class, so I'll post it to both classes. I mean day 2. Yeah, you know what I meant. So in the warm-up, you just have to work with y equals x squared, substitute that into your, put it in your graphing utility, and you get these values when substituted in. You graph it, it's an exponential. The question is, at 2, so at x equals 2, what is the slope at that location where x is 2? So here's my x-axis. At x equals 2, I approximated or estimated it to be the slope of 2. And you see I drew a line, a fake line here, well, a real line, but an assumption line based on what I thought the y-intercept might be as well. It looks like about -1. So I said the approximate equation is 2x minus 1. By the end of this lesson, we'll be able to actually calculate the exact tangent line and the exact slope to this line. So this lesson is about derivatives of exponential and logarithmic functions. It's the only two you have not finished. So you guys have done trigonometry, so the derivative of trig functions, like sine and cosine and tangent. But now we're going to expand the functions that we know how to derive. Okay. You'll notice in the first 4, I changed it from a to x to be a to u. And instead of e to the x, I changed it e to u. Log base a of x, I changed to log base a of u. And ln of x, I changed to ln of u. And the reason for doing this is I don't want to write x prime. I want you to see it as a function of u. So I'm going to use u prime, just so that there's no issue between variables and functions, so that I'm deriving functions, not just their variables. Okay, so the derivative of a to the u is quite simple. It is the same exact thing, a to the u. We then multiply it by what's the ln of my base, a, and then we times that again by the derivative of the exponent u, so u prime. All right, an example here, let me just make up an example off the top of my head. We'll do 3 to the x squared. So if I'm deriving 3 to the x squared, the derivative will be 3 to the x squared times ln of my base is 3, times the derivative of my exponent right there, which is going to be times 2x. And that is it for the derivative of a to the u. The derivative of e to the u is the same exact derivative, but it's unique, and I'll show you why it becomes unique here. So e to the u, we're going to say it's e to the u times ln of my base, which is e, times the derivative of my exponent, which is going to be u prime, the function u prime. So you'll notice that this goes away because ln of e is the number 1. So this ends up becoming e to the u times u prime. What I suggest students do is always write ln of e. because you're going to get in the habit of always writing ln of your base. ln of 5, ln of 10, ln of 12, ln of e. It is, again, the same procedure as the first one, but because the base is special, because you're lning the function e, or you're finding the natural log of base e of e, we get the number 1. So it just cleans itself up a little bit. Let's do an example. For my example, I'm going to say, the example, let's say, is e to the 2x. Well, that's going to be e to the 2x times, so this is the derivative, same exact function that you had, times the ln of the base times the derivative of my exponent, which is 2x, so which is going to be 2. This will simplify to be the ln of e will go away. It's the number 1. It's just going to be 2 times e to the 2x. I'm going to move my 2 out front. ln of e is the number 1, so I get 2 times e to the 2x. And I'm done. The derivative of log base a of u. This one's interesting. The derivative is going to be 1 over u times ln of my base a all times u prime. You'll notice that I am attaching a chain link on of u, call it u prime. This is why it's not in the denominator, but yet it's in a numerator. It's really just a whole number I'm attaching onto it, or a whole function number, right? So it's u prime over 1. I don't need to write that. I'm just attaching u prime on. Maybe you want to use parentheses. I don't know, but you're just attaching it on to the end, just like we attached on u prime here. You will also notice that just like this was a base a, this is a base a. So it's still becoming ln of a. U is just a function, so it's 1 over u times ln of a times u prime. Here is an example. Let's say I had example. Let's say I wanted to find the derivative of log base 6 of x squared. Well, that would be 1 over x squared times ln of 6 times the derivative, so the ln of my base, so it's the function, 1 over the function, x squared, times ln of 6, which is ln of my base, times the derivative of x squared, 2x. So maybe you might simplify this to be 2x over x squared ln of 6. Others of you will simplify it further. You'll get rid of x's in the numerator and the denominator, making it 2 over x ln of 6. So any of those answers are correct. We will put a correct check, check, check. These are all correct. Now, the next one, again, is special, but it's no different. What we're going to do is we are going to write ln of u as ln, oh, sorry, not ln, log base e of u. Now it follows the same procedure as the other one. So it's going to be 1 over u times ln of e times u prime gets attached onto the end. So it's 1 over the function, u, times ln of my base, base e, and times u prime. You will notice, just like above here, that ln of e becomes nice. It becomes 1 over u times u prime. Some students will even say, Mr. A, can you just put u prime over u? Be cautious. I just don't want you to make an algebra mistake. Don't forget, if there's a number out front, let's say put the number 4 out front, well, that 4 will carry all the way through. It's going to be 4 times 1 over u times ln of v times u prime. So that just be cautious of that 4 or any other number that might fall out front. So just do out the algebra, do what I did in blue here, okay? Just have that ready, do it all out, and then clean it up afterwards. Let's do an example. Let's do ln of 3x squared. This can be my example. So let's do, the example ends up becoming the log base e of 3x squared. So it's going to be 1 over 3x squared times ln of e times 6x, which after I clean it up will become 6x over 3x squared times ln of e. This becomes 2 over x, because the ln of e will go away, and then I'm left with, let me do a different color, and then we're left with 6x over 3x squared, which simplifies, I factor out a 3 and an x, and it becomes 2 over x. Okay, so again, I don't want to teach it like it's 4 separate derivatives. They are 2 separate derivatives, a to the u and log base a of u. And when I calculate using these 2 separate derivatives, this one right here and this one right here, we get special outcomes when we do ln of e or e to the u. We just get a lot more that goes away and cleans up out of it. So how are the derivatives similar? They are the same. And then we're going to say, however, ln of e becomes 1, becomes the number 1. We're going to say the same thing for this. Why did I choose to use parentheses when rewriting the above expressions? Oh, you'll notice I do this, wasn't even watching. See the parentheses here? That's because it's a function within. It's ln, not ln times 6, it's ln of 6. Just like it's ln of 3, ln of e. So we're going to say, because it is a function, because it is an inner function. Okay. Let's do our first example. You'll notice on the next page, I have them all listed. They just look a little different. Before we did a to the u times ln of a times u prime. 1 over u times ln of e times u prime. So it's all there. They just wrote it a little bit differently. I hope my notation is a little bit easier to follow. But again, these are all the same notations. You'll notice they make it look like it's 4 separate derivatives, but they're really the same derivative, where ln of e becomes the number 1. So our first example, we're going to find the derivative of this. We are going to say that if y equals e to the x plus x squared, then dy dx equals the same exact thing times the ln of my base e, times the derivative of the exponent, 1 plus 2x. It is crucial that you use parentheses right here, even though because you're indicating multiplication. you are multiplying by everything, both the 1 and the 2x. Without parentheses, it looks like you're only multiplying by the number 1 and then adding 2x to the end of it. So we want to make sure that those end up there. If you want to simplify, which I'm going to for you so you can see, here's what tends to happen. The ln of e will go away, and then you will be left with 1 plus 2x times e to the x plus x squared. Why did I move 1 plus 2x? Well, it's a factor, it's multiplication. But on top of that, you tend to see the most simple parts go in front. So 1 plus 2x is much more simple than e to the x plus x squared. So according to the calculator, so it will calculate it and rearrange it as such. Okay, example 2. So that's it. You could, the question is going to be, can I put this on my quiz? And that's fine, without the slash mark through here, and that's fine. But you can also go further and simplify it if you want to. Or if it's multiple choice, you'll have to find the answer. Example 2, at what point on the graph is a function y equals 2 to the t minus 3? For which point, at what point on the graph does the tangent line have a slope of 21? Well, that's what we're asking is when is it 21? When is the slope 21? And if it's the tangent line, what we're looking for is when is the derivative, which is the slope 21? That's the question. Oops. That's the question we're being asked. When is that 21? So let's derive it. Let's derive it with respect to t. So dy dt, let me call it y prime. The derivative of y with respect to t is equal to, the derivative of 2t is going to be 2 to the t times ln of 2 times the derivative of t, which is 1. Take away 0. There is no, the derivative of 3 is 0. So it's going to simplify to be y prime equals 2 to the t times ln of 2. Substitute in our value of 21. We get 21 equals 2 to the t. And then the last part is going to be dividing by the ln of 2. This looks really weird. Do not divide by 2, divide by ln of 2. We get a result of 21 over the ln of 2 is equal to 2 to the t power. When you go to solve this, you have to drop the t down. You can't solve for a variable. Don't find the square root, don't find the cubic root, don't try to take 1 away from the exponent. Think about it. The exponent is a variable, which means that we have to log base both sides. We can either log base e, or we can log base 10, or log base 2, whatever you want to do. You can log base anything, really. If I log base 2, it's going to get rid of the 2 as well as drop the t down. So that's an option. Another option is to just ln both sides. So I might want to just ln both sides of the equation. Let me ln both sides. So I'm going to ln 21 over ln of 2. That's going to be equal to, we have 2 to the t, so I'm going to ln 2 to the t. This will be, the result here will be, it's going to be equal to t drop down times ln of the number 2. And finally, to solve, I divide both sides by the ln of 2. And I'm left with ln, oh, this is a mess, 21 over ln of 2 all over ln of 2 is equal to time. Jeez. Okay, one step at a time. Here's my suggestion. When you enter it in your calculator, whoops, that's not what I wanted. When you enter it in your calculator, there's some things that you can do. So if you want, the first thing you want to do is be very cautious. You want to evaluate the inside here. So let me highlight. We're going to be evaluating this inside. It's also important to evaluate it correctly. So 21 divided by ln of 2. See what my calculator is doing? It's really not working well for me here. So what I want to do is I want to calculate the ln of 2 first. So I'm going to do 2 ln. Let's see. ln I'm just checking to see how this function works in my calculator. The ln of 2. So if I type in an e and I ln that, perfect. Okay, let's calculate the denominator first. You might have a graphing utility, or you might have Google. Maybe Google has a better way of evaluating it. Maybe I can just type this all into Google. I'm trying to show you on my screen. I mean, I have my utility here. Let's see, 21 divided by ln of 2. So this is equivalent. I evaluated what you see in purple there. I'm going to get rid of that calculator. I'm going to do it on my graphing utility. So it's going to be ln of 21 divided by ln of 2 is approximately 30.2965. Let's just call it 2.297. That's going to be divided by the ln of 2. It's going to be equal to time. Now, I'm leaving it in my calculator. Do not delete it because rounding, you want it to be perfect. The way to find the ln of that is to just hit the ln button again and then go second answer. And you can actually copy and paste in your answer. Or you can just go up and highlight 30.29659586 and hit the enter button as well. That will also copy paste for you. So whatever one you want to do, leave it in your calculator though. So ln of that is going to be, let's see, 21 divided by ln of 2. That is going to be 30.296. And then so ln of second answer, about 3.411. About 3.411. And now I'm going to divide that final answer by the ln of 2. And I get a result of t approximately equals 4.92. So that's the location where the tangent line has a slope of 21. 4.92. All right. So that's I'm just making sure the units are okay, good, and I'm going to open my my book, calc book, to the page where there's an answer, and it says, yes, 4.921. They round it to 4.921. That's the answer for T. I'll leave it circled. but it says at what point on the graph of the function. So that's what my t is. But then I also have to point, it says point, so it wants an ordered pair. It doesn't say at what location, it says at what point. So I also need to evaluate this into the y equals 2 to the t minus 3. So y equals 2 to that number, 4.921. 4.921, and then take away 3. So I still have this in my calculator. I'm going to do 2 to the answer that I got, and then take away 3. And I get y is equivalently equal to 27.297 rounded. And that's your point. So the ordered pair is going to be, let's round it to 1 decimal for our ordered pair, 4.9 and 27.3. It's going to be my final answer there. Guess it fits. Okay, example 3. This one, students struggle with a little bit, and then all of a sudden it clicks, and they go, oh, I get what I'm doing. There is not much that's known about this question at all, other than the fact that we have y equals ln of x. That's what's in blue right here. We also have a line. I don't know the equation of that line. All I know is that it goes through the origin. I know that it's y equals mx plus b, the b being 0, but that's about all I know. So here's what we need to do. We need to find the location here of what a is. I don't know what that location is. What I do know, it's somewhere between 2 and 3. And I also know it's unknown. So what I want to do in this example, I want to find a line with slope m that passes through the origin and is tangent to the graph of y equals x, ln of x. What is the value of m? What's the value of my slope? There's a lot of working parts here, so please follow along. What I need to do, this might seem strange, but I need to compare slope. I need to compare slope to slope. You're going to say, wait a minute, what are you talking about? Well, I'm talking about I need to compare m to being m. Wait, that doesn't really help me though. What do you mean by m and slope? I mean, we need to find the derivative and set it equal to slope. Okay, that's great. I need to find the derivative and set it equal to slope. Derivative is slope. No, well, it is. But what I want to do is I want to set my average rate of change equal to my instantaneous rate of change. Some students here have been using this term, IROC and AROC. In theory, it's no different than what I call the old school method and the new school method. IROC being the new school, this is your derivative. AROC is our old school method, y2 minus y1 over x2 minus x1. It's where IROC and AROC would be equivalent, or the derivative, our instantaneous rate of change, is equivalent to our average rate of change. When I set that equal to each other, I can actually solve for a location. Let's actually do that. Let's say that I want to find average rate of change, which is this line right here, and set it equal to my instantaneous rate of change, which is this line right here. And I want to set them equal at the same location of A. What I do know is I can find, here's my x and y. That's my x1, y1. Here, actually, I'll call this my x1, y1. 0, 0, I'll call x1, y1. And at a, comma, output, I don't know what my output is. All I know is it's ln of a. I'm going to call this x2, y2. So my old school method, my AROC is going to be equal to the slope, which is equal to y2 minus y1 over x2 minus x1, which is equal to ln of a, take away 0, all over a minus 0. That ends up being equivalent to ln of a over a. My average rate of change, or AROC, is equal to ln of a over a. Awesome. In blue, I will see how it correlates to the function. I will do the instantaneous rate of change. So IROC is the derivative, which is actually equal to the derivative of ln of a. What is this? ln of x. So I'm going to rewrite this as y equals log base e of x. So the derivative is 1 over x times ln of e times the derivative of x, which is the number 1. So my IROC, or instantaneous rate of change, is 1 over x, because this will end up going away. So what I need to do is set AROC and IROC equal to each other and solve. You know what, though? To be consistent, I'm sorry, I don't mean x. Well, I do mean x, but let's say, what is the derivative at a? Well, it's just going to be 1 over a. So let's just be consistent and keep as you see here, the slope is 1 over a, because we're using the location, instead of x, we're using the location a. So it's all the same thing. F prime of a is just going to be 1 over a. So I need to set AROC and IROC equal to each other. AROC equals IROC. So my y2 minus y1 over x2 minus x1, let me just get to the point. I'll say AROC is ln of a over a. That's equivalent to 1 over a. Well, if they're both over the same number, a, then that means that if the denominators equal each other, that means the numerators have to equal each other. You can ignore the denominators now. Just say ln of a equals 1. And this is true for just the location a. So I'm going to rewrite it as log base e of a equals 1. Use your change of base. E to the first power is equal to a. E to the first power equals a. So e to the first power equals a. So my location a is equal to e. Interesting. Let's take a look. E is the number 2.7183. What do we think? 2.7183? That's about where A is, isn't it? That's really cool. So we have A is 2.7183. But what's M? Well, M, we know, is my average rate of change, or my instantaneous. I can pick either one of these. If the number E. So I'm going to say the M is equal to 1 over x, which is 1 over e, because I know that a, the location a, is e. Or I could say it's 1 over x or 1 over a. It doesn't matter. That location is 1 over e. So the slope is 1 over e. of my tangent line. I could have also evaluated E in the numerator and denominator of average rate of change. That's just going to be ln of E, which is 1, over E, which is E, so 1 over E. It gives me the same result. At that point, AROC and IROC are equivalent, so you can use either one for that. All right. Okay. Example 6, finding the domain. This seems crazy. We don't actually have to find the derivative. We can. What we know is that the ln of 0 can't occur. So x minus 3, this value right here always has to be greater than 0. So if I solve that, x has to be greater than 3. Can't be equal to 0, so it has to be greater than 0. So x is greater than 3. State the domain of f prime. That's going to be the domain of f prime. If that's the domain for f, that also has to be the domain for f prime. So when I find the derivative, I'm going to say the derivative is equal to 1 over my function, times ln of my base e. Don't forget, hold on. Don't forget that this function is equivalent to log base e of x minus 3. So it's 1 over my function times ln of e times the derivative of my function, which is 1. So when simplified, I have the derivative is equal to 1 over x minus 3, where x is greater than 3. If you graph 1 over x minus 3, you're going to have an issue at 3. You see it, 3 minus 3 is 0. There can't be a number there that of 0 in the denominator. But 1 over x minus 3 is going to graph in 2 quadrants. And with those quadrants, we can only use numbers that we receive that are greater than 3. So that's my domain of example 6. Okay. Let's see, number 4, going the long way with the chain rule. Let's see, I don't know why they would consider, oh, there's a lot going on with this one. Let's come back to this one. Yeah, we can do this. All right, we're just gonna have a lot going on with, let me see if the book has any other strategies than what I'm thinking. For example, 4. Nope, just a lot of chain rule. Okay, 1 over Yep, okay. All right, well, let's just do this one out. So dy dx, just bear down. This is a long problem. It's going to be 1 over my function, which is a to the sine x, times the ln of a times the derivative of a sine of x. So the derivative of a sine of x, again, now is a number to a variable exponent. So it's going to be the same thing, a sine x times ln of a times the derivative of sine x, which is cosine x. Now, when this is going the long way with the chain rule, it kind of almost means it's almost like a double. It's actually a double. What we have here is you have this initial idea. Then you have your u prime. This is my u prime. When I derive it, I'm deriving it in exponential. So I'm deriving both an exponential that has chain rule and a logarithmic function all at the same time. So I have two two things going on here. So I'll leave that label of u prime right there. U. I'll leave that one as u. That whole thing as u. All right. Now, when I clean it up, I get dy dx equals a to the sine x times ln of a times cosine of x all over a to the sine x times ln of a. Well, this cleans up quite nicely. Because it's all multiplication, it works. And we are left with dy dx as a final answer, dy dx equals cosine of x. And that's it. If you think about the theory behind this one, I mean, this is a theory-based question. So if I were to rewrite this using my, let me recopy it down over here. This is really cool. Watch this. We could have made it much more simple. This is a to the sine x. If I use my my change of base, a to the y is equal to a to the sine x. If they both have the same base, then that means that the exponents also have to be the same. So y has to equal sine of x. That's a simplified version of this. What's the derivative of y? dy dx. What's the derivative of sine? Cosine. So you notice in two very different ways, we get the same derivative using our rules. That's why it says going the long way with it. Now I see that if I were to just rearrange it, it would have derived nicely as well. Knowing that my bases are the same, so my exponents have to be the same. All right, using the power rule in all its power. Whoa, okay. So in this one, we're going to, in example 5, we have x to the square root of 2. So in this case, we are going to just say dy dx is equal to the square root of 2 times x to the square root of 2 take away 1. Now that does not fall under the radical, it falls on the outside of the radical. And we're done. That is it, because there's nothing we can really, oh, I'm sorry. I said the square root of 2, I wrote the square root of x. Square root of 2, I dropped my exponent down, I took one away. See how this differs? Because it's only the square root of 2 in the exponent. It's not a variable in an exponent. So it doesn't follow the pattern of what we're doing today. And this one, again, this one won't because the exponent's pi. So you see how this one follows the regular pattern. Pi times the inside to the pi minus 1. And then don't forget to put on your chain link here of the derivative of the inside. The derivative of 2 is 0. The derivative of 3 sine of 3x is 3 cosine of 3x. And then we derive the innermost 3x, so times 3. Notice that these don't involve either the exponential, derivative of exponentials, or derivative of logs. All right, this one is a flu one. Yikes, this one is intense, but it's the last one before you start your practice problems. Don't worry, you don't need to expect one like this on your quiz. Let's see. Let me do. I think you should be good with these. They have all the answers. So I'm gonna let you try these all on your own. The answers are all here in simplified form and in the unsimplified form. Okay, but I'll do this one last example and then I'll call it a day. How fast does a flu spread? The spread of a flu in a certain school is modeled by the equation P of T equals 100 over 1 plus e to the 3 minus t, where P of T is the total number of students infected T days after the flu was first noticed. Many of them may already be well again at time t. So it wants us to estimate the initial number of students affected with the flu. Let me see. Infected, the initial infected. Well, according to this scale, these are x's, these are y's, these are intervals. Looks like -10 is right here, -20. This looks like -25. It's half of it. So 0. So that's 10. So it looks like the initial amount was about 5. So we're going to say 5 students were infected with the flu. 5 students. Let's say about 5 students. How else can I figure this out? Well, I can actually evaluate P of times 0, right? So I can do 100 over 1 plus e to the 3 minus 0, which is, I'm just going to get rid of, no, I'll write it once more. P of 0 equals 100 over 1 plus e to the 3. I'm going to do that on my calculator. E to the 3 is about 20.80855. So I'm going to add 1 to it. So I have approximately equals 100 over 21.086. So 100 divided by that answer equals about 4.743. So yeah, we're going to say about 5 students because we're going to round up to 5. Can't really have 4.7 students. How fast is the flu spreading after day 3? So we're going to say P of 3. We have, it's important that we don't evaluate, what does the book say at time 3? Yeah, so we want to make sure that we find the derivative because it says how fast is it spreading. We don't know, we don't want to know how many people. If I evaluate 3 in time, it's going to tell me P of T, which is the total number of students infected. I don't want to know how many students are infected. I want to know the derivative of P with respect to T at the number 3. So I'm going to find dp dt, the derivative of P. It's going to be the denominator, 3 minus t. Yep, so the denominator minus the times the derivative of the numerator. The derivative of 100 is 0. Minus the numerator, 100, times the derivative of the denominator. So e to the 3 minus t is e to the 3 minus t times ln of e times the derivative of negative t, which is -1. all over denominator squared. 1 plus e to the 3 minus t quantity squared. You'll see that this goes away with 0. You have this goes away at the number 1. You have a negative 1 times a negative 100. So this ends up becoming 100 e to the 3 minus t. Because that's your negative 1 times negative 100 is 100 times e to the 3 minus t. So it's 100 to the 3 minus t all over 1 plus e to the 3 minus t quantity squared. Now we're going to evaluate dp dt to be at the number 3. Is that what they wanted? After 3 days. So we're going to evaluate this at 3. So let's say p prime. Let's just call it p prime at 3. It's going to be 100 times e to the 0 over 1 plus e to the 0 squared. E to the 0 is 1, so it's 100 times 1 over, it's going to be 1 squared, so it's 100. So it's increasing at the rate of, so dp dt at 3 is 100 students let's see. I'm sorry, I made an error here. I'm looking at the textbook and I see what I did wrong. Take a look right here. That's 1 plus 1, not 1 plus 0. My apologies. So this is going to be, let's clean that up. It's going to be 2 squared. So 100 divided by 4 is 25. So it looks like it's increasing at the rate of 25. How fast is the flu spreading after 3 days? We're going to say p prime at 3 is equivalent to 25 students per day, or 25 cases per day. Okay. When will the flu spread at its maximum rate? What is this rate? So we are looking for this right here. It looks like it's about 3. Do they have, nope. They found it by tracing. We don't know how to find the maximum rate yet. This is going to bring us into our next unit. So instead of me teaching you that now, let's leave this open-ended and say, we're going to say max rate of 25 students per day on about day 3. Awesome. Oh, someone's beeping at me outside. All right. So we have, this was the entire lesson. I'm sorry it was long. Everyone is still accountable for taking their quizzes on time. This video will be a resource to help you prepare. Practice, practice, practice makes confident. Do all these problems. So your homework is to do this CUDA worksheet 1 through 24. So we'll do practice in class numbers 1 to 24 for homework. Homework numbers 1 to 24. I think There's also some textbook problems. I put textbook in here. Nope, there are no textbook problems. There is, though, the other homework is the, hold on one sec. So, whoops, nope, cancel. CUDA homework, and then it's also the Unit 5 Quiz 2 review. Okay, so we have plenty of time. Day 2 students, you'll take the quiz on Thursday, and day 1 students, you'll take it Friday, and we'll chat in class during our next class. Okay, and I can help you with any questions if I have. Okay, have a great night. Take care.